Hi, this is Jiayi Wei from UT Austin. In this video, I'm going to introduce our recent work on simultaneous state estimation and dynamics learning from indirect observations. To motivate our problem, imagine that we are trying to model the dynamics of this outdoor autonomous car. As you can see, there are complex interactions between the tires and the ground, involving small objects like grass and leaves. And sometimes, when the car is turning fast, there can also be sideways sliding. These effects are generally very hard to model and can significantly alter the car's dynamics. There are mainly two approaches to deal with such situations in the robotics field. The first is to manually design some simple mathematical models which can be imprecise and assign a large prediction uncertainty to account for the inaccuracies. And the second approach is to automatically learn complex models with supervised learning techniques. However, such techniques require high-quality state trajectory data, which may not always be available in robotic settings, such as outdoor off-road navigation. In this work, we propose a new way to relax this data requirement by focusing on learning dynamics from noisy or indirect observations. These observations can be anything, like range-bearing readings, LiDAR scans, camera images, and so on. And we can connect these observations with the underlying robot states through an observation model. We also assume the robot dynamics is Markovian, with an unknown mean and variance. Since the observation model is not the focus of this work, we assume it is given and focus on learning the dynamics. However, the lack of robot states poses some special challenges. In particular, we now have a chicken and egg problem. On one hand, we need high-quality state transition data in order to fit an accurate dynamic model. But on the other hand, we need a good dynamic model in order to perform state estimation. This motivated us to take an iterative approach to break this mutual dependency between these two tasks. Instead of solving either task independently, we apply the expectation maximization algorithm and put the two tasks in an iterative loop, in which we will start from an inaccurate dynamic model and alternate between two steps. In the each step above, we combine the current dynamic model and the observations to estimate new state trajectories using posterior sampling techniques. And in the M step below, we update our dynamic model to be more consistent with the sample trajectories using stochastic gradient ascent. In more details, our algorithm STEADY works as follows. In the initialization step, we can start with a dynamic model that's very simple, such as a Brownian motion with large variances. Then, in the E step, we sample a fixed number of state trajectories from the posterior state distribution. This can be done efficiently using classic algorithms such as particle filtering. In the M step, we compute the log joint likelihood of the trajectories that we just sampled, and then update our model by performing one step of a gradient ascent. Note that here we view the sample trajectories as optimization constants when performing the gradient computation. And from then on, we can iterate between the two steps until convergence. What's cool about the EM algorithm is that by alternating between these two tractable steps, it is guaranteed to improve the marginalized data likelihood over time, even though this marginalized data likelihood itself is generally intractable to compute, since it requires integrating over the trajectory space. In our experiments, we parameterize the unknown dynamic models using the following neural network architecture, which predicts the mean and the variance of the state derivatives in the robot's local reference frame. To sample the posterior trajectories, we first use the standard particle filter to obtain the state samples at each time step. We can then sample each trajectory sample by first picking a particle at the last time step and then tracing back its ancestral lineage, as shown here. Now, let's see how steady works in action. Here, the origin line shows the ground truth positions of an autonomous car, and the observations consist of the bearing readings of 4 landmarks relative to the car's orientation. We can see that the inferred blue posterior gradually improves over time and gets closer to the ground truth as we run steady for more iterations. In our main experiments, we evaluate steady and 4 other baseline techniques on data collected from both simulation and real-world robots. And our results show that steady significantly outperforms all other approaches in both state estimation and forward prediction tasks. We can also visually compare the posterior velocities inferred by steady and another learning approach that relies on a handwritten dynamic model. We see that our iterative approach produces results with much higher quality and avoids the biases caused by the incorrect modeling assumptions in the handwritten model. To study how the learning outcome is affected by the observation model, we vary the amount of noise in the data and compare the errors of different approaches. As you can see from this graph, not only does steady perform the best under all noise settings, but as the noise gets smaller, its performance also converges toward the same level as by learning directly from the true states. Please see our paper for more details, and our implementation is also publicly available on GitHub. Thank you for listening.